All right, so with our second part of the notes, before we start looking at logarithm properties and the type of questions you need to see, it's helpful for you to understand that there is a need for logarithms. Logarithms can do something that other functions can't do. So if I ask you to solve this guy, 2 to what power gives you 4, I hope that you could do that in your head. Because the answer is a nice whole number, it's not an issue. But if I ask you to solve this one on the right, 2 to what power gives you 5, well, that's not a nice whole number. 2 to the second power gives you 4, so this one's going to be more than that. 2.1, 2.2. It's actually 2.322. But you're not going to come up with that in your head, number one. And number two, the higher you go in mathematics, the more an exact answer matters. A rounded answer, not going to be good for building anything. Can't have a bunch of rounded answers. So logarithms and their properties help us figure this out, how I was able to get that and the exact answer. Okay, so one thing you need to be able to do, and this is probably how it would show up on the ACT, or one of two ways it would show up on the ACT, but switching back and forth between what's called exponential form to logarithmic form. So these 4 questions are in exponential form. There's some sort of exponent going on there. Logarithmic form is going to have log in the answer. Okay, and you have to move a couple things around for you to be able to add that log in front. You can't just put the log in front and expect it to work. So the exponent needs to switch with the other side. And then this base becomes the logarithm base. So the way I visualize that is the 2 and the 9 are switching places so that I can throw a log sign out front. So B and C could switch places. And then that allows us to put log out front. 2 and 6. 15. Switch X and 5. So these are the logarithmic equivalent of those exponential forms. Okay, so not difficult. I mean, you're literally switching 2 numbers around and writing log out front. But if you start off with something in exponential form, sometimes we like to write it in what's called logarithmic form. Okay, you need to be able to go the other direction as well. So if you really understood the first one, then you're just saying, all right, for me to remove the log, I need to switch these 2 back. So 3 squared equals x. A to the b power equals c. 8 to the x equals 11. And 2 squared equals 4. So again, you're just switching the 2 numbers around. Now you have to make sure you know which ones, but you switch them if you want to add log out front, or you switch them back if you want to take the log away. So these would be the exponential form. So again, of the 2 ways I would expect to see this on the ACT, that's probably one of them. And if you've seen logarithms on the ACT and you had no idea what to do, I mean, that's kind of understandable with the AMI stuff you guys had last year. But you can see if it was one of these questions, hopefully you would get that next time, because they don't take a lot of work, not difficult, you just have to practice and recognize it. Okay, any questions about switching back and forth between these 2 forms? Okay. Okay, so in each of those questions, log had some sort of base. Now there's the most common two type of logs don't have a base. And by the way, this is what's in your calculator as well. If you look at your calculator buttons, there's a log button, and then there's an ln button. Log and ln. So they're just assuming that if you're working with logs, you know this. So maybe you don't because you haven't heard it before. But natural log ln, which is for natural log, means log base e. So these two things say the same thing. Natural log just means log base e. That e number that we've been talking about lately, 2.719. And when there's not a base written, this is called a common log. That is assumed base 10. No base written, that's assumed base 10. So these two things are saying the same thing, and these two things are saying the same thing. So, until you feel a little more comfortable with logarithms, anytime you see no base, you probably should just squeeze in a base of 10 to visualize it. And anytime you see natural log, you should probably just rewrite it as log base e. Since those are the same thing, that makes them a little easier to work with till you feel comfortable. Let's see if I can get it pulled up. Yeah, so right here in a little bit, we'll talk about how to deal with the calculator when you're trying to approximate. Here's the log button. That one, come on, but log button, but that's going to assume base 10, and then right below it, ln for natural log assumes base e. Okay, and you should be able to evaluate some without a calculator, so we will ask you to do this. So, like the one I did at the top of the page that was some weird decimal, can't really do that in your head, but something like this you can. Now the trick to this is really just understanding what this is asking, and I'm going to show you this two different ways because it might make more sense to some people one way than the other. When I read this, I just see it as it's saying 7 to what power gives me 7. The exponent of what to that base gives you what you're taking the log of. So the answer to that's 1. 7 to the first is what gives you 7. That's how I'll usually verbalize it, because I can't verbalize the other way I'm going to show you, but you're welcome to do this as well, to kind of make a connection here. Let me set it equal to x, and let's pretend like we're trying to solve this. This is logarithmic form, because it has a log in it. If I switched it to exponential form, the 7 and the x switch places to make log go away, and then it's phrased in the same way that I said it out loud. 7 to what power gives you 7. If it's really something that you can do without a calculator, then it should be one that we should be able to do in our head. Okay, so this guy is just really asking 3 to what power gives you 27. So 3 to the first is 3, 3 squared is 9, and 3 to the third is 27. All of that equals 3. So even if you saw that on the ACT, I'm going to show you how to type it in the calculator here in a bit. But even if they did, it's so much quicker if you just understand how to work with it. You could do it without picking up a calculator. All right, over here, no base is written, so let's squeeze in a base 10. This is really just asking 10 to what power gives you 100. So the answer to that is 2. The log of 100 is 2. I have to fix that. Since natural log means log base e, that's asking you e to what power gives you e, and so that would be 1. Anything to the first power gives you the same thing. E to what power gives you e. So as soon as you kind of understand what question you're supposed to be asking yourself, you don't really have to write down much besides the answer on these. This is saying 10 to what power gives you 10? Well, that would be 1. E to what power gives you 1? That would be 0, because anything to the 0 power is 1. 10 to what power gives you 1? Well, again, 0. Anything to the 0 power gives you 1. You will 100% see that on the quiz and the test. And then sometimes they're a little trickier here with like some fraction work. This answer couldn't be 1 because 2 to the first is 2. But if I want the reciprocal of that, 2 to the negative 1 is the same thing as 1 over 2 to the positive 1. So negative 1. That one's a little harder to see at first, but what you probably need to add to your notes here is you should be asking yourself, 2 to what power gives you a half? That's the question you have to ask yourself, but give yourself a chance to know that the answer is negative 1. Okay, so how do we evaluate these when we do have a calculator? If we're interested in rounding to a decimal, or we want to know about how much it is because it's not exact, there's a formula called change of base formula, and you are expected to know this formula, even though there's kind of a shortcut in your calculator for some people. But even in like college algebra, they still will test you over change of base formula. They expect you to know that. So if your base is 10, you're in good shape because your calculator is set up to do base 10. If it's just a natural log problem, your calculator has that built in too. But if it's a base other than 10 or a base other than 3, or E, then you have to do the change of base formula. So this is the same thing as log base 10 of 7 divided by log base 10 of 3. It's also equal to the natural log of 7 over the natural log of 3. Since your calculator has these two built in, you could type in either one of those into your calculator. Log of 7 divided by log of 3, or natural log of 7 divided by natural log of 3. It's about 1.771. Okay. So change of base formula would say that this is the same thing as log base 10 of 27 over log base 10 of 5, which is also the same thing as the natural log of 27 over the natural log of 5. You do need to know both. Even though you really only need one to type in your calculator, as multiple choice, sometimes it might be written like this, sometimes it might be written like that. We have done that in the past. And then you could use your calculator to round. Okay, so my calculator program's not working, but if you had your own calculator out, if you hit alpha window, some of you will have an option for number 5 that says log base, and log base does let you type it in the way it looks, like it lets you squeeze in a base of 3 or a base of 5, but that depends on what calculator you have and how updated it is. And you will still be tested over change of base, so you still need to practice this. But just know that there is a workaround in your calculator. So back to the start. This is how I did this question just a minute ago. I've applied a couple skills that we've now talked about. I saw that this was not solved for x. This is exponential form. I considered switching it to logarithmic form. So I can put log in front as long as I switch the 5 and the x. So the exact answer to this first example is log base 2 of 5. The way I got that as a decimal is in my calculator, I said, what is log of 5 divided by log of 2? And that's how I got an approximation. So switching from exponential form to logarithmic form and knowing the change of base formula to type that in is how I was able to estimate that answer.
So how do you want us to answer on the test?
Well, this quiz would be no calculator, so you would just stop there. X equals that. it'll be very similar to worksheet 1, so we'll look at those examples. It doesn't come up too much like that, I don't think. Okay, there's some other properties of logarithms that are often going to be useful, and here's a couple examples. This property, so generic numbers a, b, and c, if you have an exponent on something that you're taking the log of, that exponent can come down out front. And this is a super important idea to us because we just did exponential functions. Sometimes you need to solve exponential functions. There's lots of real-world examples to exponential functions, and occasionally we want to solve for something in the exponent. For example, those compound interest formulas. They had the rate in the exponent, they had the time in the exponent. If you wanted to solve for one of those, you need logarithms, you need this property. So what I mean by that is, let's look at this one. If I'm trying to solve this for x, what value of x makes this true? I could use this property. I could also switch from exponential form to logarithmic form, and either one's okay. But imagine if you took the log of both sides, which is okay because you're doing it to both sides so it stays equal. This property that I just gave to you said if it's an exponent on something you're taking the log of, which x plus 2 is an exponent on 4, which I'm taking the log of, feel free to bring that down out front. And that is very significant because this is the only time in mathematics where you're able to pull an exponent down. You're trying to solve for x, your normal PEMDAS stuff isn't super helpful. It doesn't get it out for you. Logarithms will. Okay, and then we just solve it like we'd normally solve. Undo times with divide, undo plus with minus. But this property allows me to get an exponent or a variable out of the exponent. Okay, I meant to make an extra example there, but I didn't do that. So when we get to worksheet 1 in just a minute, they're basically going to be phrased like this. I'm just trying to give you an example of why you really need to know that property. Okay, another property that most years we just kind of say, well, you really need to know this. Here's how you get the answer. Make sure you recognize the pattern. And it doesn't really apply too much until calculus, but you do need to know this property. If you have some number a and its exponent is a log and its base is the same number, so notice these match, of something like b, all of that just simplifies to b. Now, if you're interested in why that works that way, you need to know a little bit more logarithms. I could answer that question for you a week or two after spring break, but you've got a number like 3, and in the exponent, it's log base 3 of something. All of that will just be the something. Not hard questions to deal with, but you do have to recognize that pattern. Okay, so instead of just saying, hey, you're going to use this in calculus someday, here's an example, and they've been having to do this recently. If you needed to solve this equation for y, there's not like an algebraic step that lets you just undo a natural log or undo a log. So you can do what's called exponentiating, which is where you make the left side an exponent to something, and you make the right side the exponent to the same thing. So like the left side becomes the exponent on e, and the right side becomes the exponent on e. And you might say, well, why in the world would you do that? Well, you've never seen anything like that, but it does come up in calculus. Because now this is this property up here. I've got a number e, its exponent has a log of the same base, natural log means base e, of y, So all of this just becomes y. That's the only way to change it to a y. So you don't have to exponentiate both sides. That's not going to come up for us. But I'm trying to show you that this property, even though it seemed kind of random to you today, it does have its uses. Okay, evaluating using log properties, exponent rules. So I think these are all ones that we should be able to do in our head, no calculator needed. But they're not written very nicely. So first off, if there's no base, you might squeeze in a base of 10. If it's natural log, you might make it say log base e. Base of 10, log base e, if that bothers you. Well, so this is saying like 10 to what power gives you 1 over x to the 5th. And that's hard to do in your head. So maybe you should first rewrite the question. Instead of 1 over 10 to the 5th, maybe it's 10 to the negative 5th. So usually when you have a negative exponent, you move it to the other side of the fraction bar and make it have a positive exponent. But in this case, it kind of makes sense to bring it up. And now we can say, well, one property we talked about was if you have an exponent on something you're taking the log of, feel free to bring that down out front. And then log base 10 of 10 is something that you should be able to do in your head, because it's just saying 10 to what power gives you 10. So in the end, all of that mess comes out to be negative 5. But I hope that you see, and part of what makes logarithms kind of difficult is if you know most of the properties or you're pretty consistent with them, you can still miss questions, because I had to do several different things. I had to know the base was 10. I had to do an exponent rule, which isn't really logarithms. I had to know this property of logarithms, that this negative 5 could come out front. And I had to know how to evaluate that. So there's 3 different things keeping me from that answer there. 3 different new things. Okay, over here, instead of saying 1 over e to the 7th, maybe just say that's e to the negative 7th. Then you could bring the exponent down. And log base e of e should be 1. Negative 7 times 1 is negative 7. Okay, so this might be a good time to pause and make sure that you are seeing those steps. Or if you need me to go over them a little slower, that would be fine. You guys following those steps? Okay, so same thing on these two, but just a common mistake that I've seen from students in the past. Like if you wanted to rewrite this one and work it the same as those up here, you can move this to the numerator and give it a negative exponent. But if you do that, it's not just the x that's negative, it's the whole exponent that's negative. So you have to distribute that negative. The minus 1 becomes a plus 1. Now this is an exponent on something that I'm taking the log of, so this whole exponent can come down out front. What's left behind is log base 10 of 10, which is 1, because again it's just asking you 10 to what exponent gives you 10, so all of this becomes 1. So the answer to that question would be negative x plus 1. So again, if you're moving something from one side of a fraction to the other, the whole exponent changes sign, not just the first term of the exponent. So a negative 3x and a minus 2. Exponent on something you can take the log of can come down out front. Log base e of e is 1. There's our answer. Okay, and then we're going to do a quick sketch of the logarithmic functions. We talked about this last time. We talked about, and I don't want to do the whole process again. You definitely should have watched those videos by now. But I did talk about 3 to the x was the inverse of log base 3 to the x. So you could graph 3 to the x, switch x and y of each of those points, and you discover what log base 3 of x looks like. So we did that for a couple last time, and it looks something like this. And regardless of whether your base is 3, or your base is 5, or your base is e, or your base is 10, they all basically look the same. Just like all the exponential growth equations basically look the same. These all have an exponent of 1. They all have a domain of 0 to infinity. The only thing that really changes is how quickly they hug up to this axis and how quickly they rise over here. But generally speaking, they all look the same. All right, so each of these also have a vertical asymptote. So notice this vertical asymptote is at x equals 0, x equals 0, x equals 0, x equals 0. It's the vertical line that your graph can never touch, but it approaches. So, okay, well, here's that one. Now, I don't want to regraph this, but this plus 4, we're supposed to know that that shifts our graph left 4. So if the asymptote was at x equals 0, and I shift my whole graph left 4, it should now be at x equals negative 4. Everything moves left 4, then so does the vertical asymptote. This is the one that has given people issues before, but if you put a negative on the x only, that's how you reflect over the x-axis. But you might want to think of it like this, because reflecting over the x-axis, y-axis, doesn't change the vertical asymptote. If I flip this over here, the vertical asymptote is still at x equals 0. If I flip this over to here, still the same, still the same, still the same. So I'm not worried about that, but if you flip over the y-axis, this rule changes. You're used to adding 4 to x, making it go left 4, but really this negative has gone to both of these, so this is actually right 4. And that's not usually something that comes up much in Algebra 2. They just kind of avoid those questions for you. But the rules for right and left switch if you're reflecting over the y-axis. So if the vertical asymptote was at x equals 0, and then this is making it go right 4, its vertical asymptote would be at x equals 4. This one would have a vertical asymptote at x equals 0, because that's where all the parent functions have it. Reflecting it over the y-axis doesn't change that. This usually makes it go left 7, but because of this, it's actually going right 7. So if the whole graph has gone right 7, the vertical asymptote has moved right 7 too. Again, it should be at 0 by default. So in the end, if it's going right 7, it's moved right 7 too. And then last piece of our notes before we can practice some of this is there's a few questions that are a little tricky. You need to realize that it's not possible to take the log of a negative number. So if you look up here, We never took the log of a negative number at any time. Log of a negative number just doesn't exist. So we'll be solving things like this one, and before the second half of the test we'll do harder equations, but these are kind of rigged. Log base 3 of some stuff equals log base 3 of some stuff. Those are only going to be equal if the inside stuffs are equal. So you can set those equal to each other, subtract an x from both sides, subtract a 5 from both sides. You get an answer, but there's a chance that it's extraneous, which just means like your algebra reasoning is good, but it created an answer that doesn't actually work. So you have to consider plugging it in to verify that it's okay. So if I plugged it in over here, I would get log base 3 of 3. That's not a problem because I can take the log of a positive number. If I plugged it in over here, this would be log base 3 of negative 2 plus 5, which comes out to be 3. And so that one's good. Not only did I check to see that it make the left side equal the right side, but there's no, it also shows me that it wasn't extraneous. It's a real solution. I would keep that. Whereas over here, if I tried the same thing, log base 3 of some stuff equals log base 3 of some stuff. Those will be equal if the stuff is equal. So you go to set those equal to each other. You say, okay, well wait, that's a quadratic. Quadratics really need to be all on one side set equal to 0 to solve. You factor that, you see that negative 3 makes this equal 0, and positive 1 makes that equal 0. And if you're not careful, you circle both of those, and you just lost half credit, because really only one of them works. Not that I did anything wrong. I solved the quadratic correctly. My first step approach was good. I'm not just doing some careless thing. But look at what happens when you plug it in. And this is the only way to check for extraneous answers. Plug in negative 3 to both sides. You would get log base 3, log base 3. Negative 3 here would be 9 minus 3. And negative 3 here would be negative 2 times negative 3. Okay, that works. That's a true statement. There's no issues with negative 3. But when I try to plug in 1, this would be log base 3 of negative 2, and this would be log base 3 of negative 2, which sounds okay, but you cannot take the log of a negative number. Logs don't exist for negative numbers. You can't have log base 3 of negative 2. This is asking you 3 to what power gives you negative 2, and it never does. So this is what we refer to as extraneous. Like our algebra steps are correct, our reasoning was correct, it just doesn't solve the original equation, which was the whole point of the question. So we often need to plug those in to test. Alright, so that's quite a bit of information for once, but let's go ahead and switch over to worksheet 1. So we're going to do all of worksheet 1 together, and then worksheet 2 is the one worksheet 2 will be your homework, but it's very similar to worksheet 1.